Welcome to Maths for You channel, a past question on pure mathematics from Sri Lankan A-level past paper. Part A, let P is an element of real and P is less than or equal 1 and greater than 0. Show that number 1 is not a root of the equation p squared x squared plus 2x plus p equals 0. Let alpha and beta be the roots of this equation. Show that alpha and beta are both real. Then write down alpha plus beta and alpha beta in terms of p and show that 1 over alpha minus 1 times 1 over beta minus 1 equal p squared over p squared plus p plus 2. Show also that the quadratic equation whose roots are alpha over alpha minus 1 and beta over beta minus 1 is given by p squared plus p plus 2 times x squared minus 2 times p plus 1x plus p equals 0. And both of these roots are positive. We'll come to that later on. Let's deal with the first part. So I just took that function as fx equal. The reason why I want to use the reminder theorem. P squared x squared plus 2x plus p equals 0. This we need to prove that 1 isn't a root. What I'm going to do, I assume 1 is a root. Assume 1 is a root. Is the root or 1 a root? If that's so, that the reminder theorem tells us f1 should be 0. Right, see, if we prove that f1 is 0, 1 is a root, but we're going to prove f1 isn't 0. Therefore, 1 isn't a root. So f1 equal, substitute 1 for x, so p squared plus 2 plus p. Then I just sort of rearranging it. I take p out, p times p plus 1, 2. P, we have been given, p is greater than 0. So p is greater than 0. Therefore, p plus 1 must be greater than 0, and p times p plus 1 must be greater than 0. So p plus times p plus 1 greater than 0, and add 2 greater than 0. All it is, f1 isn't 0. Therefore, 1 isn't the root of p squared x squared plus 2x plus p equals 0. So it's the first part done. Then alpha, beta are the roots. If they are, we need to prove, first of all, we need to prove they are real. Okay, alpha, beta, p squared x squared plus 2x plus p. So this is a quadratic equation. So for the root to be real, the discriminant must be greater than or equal. If it's the real and different, greater than. Well, let's see. As long as we prove that greater than, that's good, or greater than or equal, is good. So the discriminant of the, say, if a function or equation ax squared plus bx plus c equals 0, then the discriminant is b squared minus 4ac. So that is exactly what I just saw, the discriminant of that equation given, or the quadratic equation given. B is 2, so 2 squared minus 4 times p a is p squared times c is p. Therefore, 2 squared is 4 minus 4p cubed. Take 4 out, and 1 minus p cubed. P is less than 1, less than or equal 1. So less than or equal 1. Therefore, right, okay, less than or equal 1. Therefore, p cubed is less than, let me see, is it less than or equal, isn't it? So let's use that less than or equal. And p cubed must be less than or equal 1. Less than or equal 1. If it's 1, 1 is 1. So the less than or equal 1. If it's less than or equal 1, if say this is 4, if in case the p cube is less than 1, so 1 minus p cube is positive, therefore 4 times positive is positive. But if p is happen to be is 1, therefore 1 minus 1 is 0, so that is 0. So that's 0. So both roots are real. So greater than or equal 0, both roots are real. Because of the discriminant is greater than or equal 0. Therefore, both roots are real. They could be different real or same. That we didn't go into that. We just want to prove both are real because of the discriminant is greater than or equal 0. Therefore, the roots must be real. Okay, next one. Alpha plus beta. So alpha beta is given. We need to prove alpha plus beta. So we know the alpha, if it's an equation, say ax squared plus bx plus c, it is the equation is, if the root is alpha plus beta equal minus b over a, alpha beta is c over a. This is a standard formula of a property. It's just given here as well. Right. So alpha plus alpha plus beta equal minus b over a, which is minus 2 is the b, minus 2 over p squared. And alpha beta, c over a, is p over p squared, is 1 over p. So this is these two. Right, now we need to prove 1 over alpha minus 1 times 1 over beta minus 1 equal p squared over p squared plus p plus 2. So we need to prove it. So let's take the left-hand side. That is 1 over alpha minus 1, beta minus 1. If you expand it, alpha times alpha beta minus alpha minus beta, take minus out, alpha plus beta minus times minus 1. The minus minus 1 times minus 1 is plus 1. So nominator 1, alpha beta, we have, we know that 1 over p, and alpha plus beta, that is minus 2 over p. So alpha plus beta minus plus 2 over p squared plus 1. Keep it numerator, the denominator take LCM p squared. So p plus 2 plus p squared, and flip it over. There's two questions, divide one another. So p squared over p squared plus 2. This is what this one is. 1 over alpha minus 1 and beta minus 1. So we just proved it. Right, now look at the question. The question, show that the quarter equation whose roots are alpha of alpha minus 1 and beta of beta minus 1 is given by p squared plus p plus 2x squared times x squared minus 2 p plus 1 times x plus p equals 0. So the roots are given in the form of alpha and beta, but we need to prove, or we need to find the equation. Right, let's deal with it. So start with, these are the two roots. These are the two roots. If we multiply, no. This is we need to prove it. That's done, isn't it? Yeah, sorry. These are the two roots. So alpha minus 1, beta minus 1. So first of all, I just wanted to add them together. So the two roots add, we know that the equation ax squared plus bx plus c equals 0. The alpha plus beta equal minus b over a, alpha beta c over a. This is a root. The addition of roots is minus b over a. Addition of the multiple of roots is c over a, but not alpha beta. Just for an example. Right. So what we have are just addition of roots, which is alpha of alpha minus 1 plus beta of beta minus 1 on the right hand side. The left hand side is standard b over minus b over a, but we keep that. We'll put it later on. Just b over a, which is, we need to find the equation, don't we? So the minus b over a. So we can find that the equations minus b over a format. If you add them, the LCM is alpha minus 1 times beta minus 1. So the denominator become alpha times beta minus 1, beta times alpha minus 1. So I just purposely taking 1 over alpha minus 1 times beta minus 1. And the nominator, alpha, same, keep it. But we know for sure that we have, from the first part, we proved it, this one, the p squared over p squared plus p plus 2. So instead of that, I just substitute that p squared over p p squared plus p plus 2 time. Here, if you do that, the nominator, alpha times beta, another alpha times beta, therefore 2 alpha times beta, alpha minus alpha, and minus beta. So minus taking out alpha plus beta. So this is, so 2 alpha times beta is 1 over p, so 2 alpha times beta, 2 over p. And alpha plus beta minus 2 over p squared, so minus minus plus 2 over p squared, that one. Simplified, if we could take this, one sec, right, it's plus. So if you do that and that, for the first part, the second part, both of them gone. I might as well leave it like that to work it out, otherwise confusing. All right, okay. If you multiply p squared over p squared plus p plus 2 times 2 over p, that will be 2p over, because 2 times p squared, 2 p squared, and p cancel out, 2p over p squared plus p. Then if you multiply p squared over p squared plus p plus 2 times 2 over p squared, then p squared cancel, 2 over that. So if you take add them together, so denominator same, therefore 2 plus 2p plus 2, that is 2 times p plus 1. That is the addition of the roots. Then now it's multiple of those roots. So C over A. So we have found, whatever the equation is, we have found minus B over A here. And now we try to find C over A. Right, alpha times alpha minus 1 times b over beta minus 1. Again, alpha beta, you don't need to go a lot further. It would be a lot easier if I would have done it. Anyway, okay. Alpha beta is 1 over p. Then this, if you do that, if you same as before, because we know the 1 over alpha minus 1, beta minus 1 equal p squared over p squared plus p plus 2. As we can substitute that. So that is the denominator. So 1 over, so p squared over p squared plus p2. Then alpha beta, that is 1 over p. That is pp cancelled out, that didn't cancel out. So we have p divided by this. So C over A done. Now, from it, if we compare it, this is minus b over a. This is the new equation is minus b over a. This is c over a. Right. If you look at it, the denominator is p squared plus p plus 2. So A is this. Then C, p over C is p. Comparing it. So B here, 2 times p plus 1. That is 2 times p plus 1. That's, so we know A, we know B, we know C. This A squared plus bx plus c. That's the standard equation. We know A, we know B. Right, we put that A is p squared plus p plus 2 times x squared minus B is minus 2 times p plus 1. So minus 2 times p plus 1x plus c is p. If you look at it, this is exactly what we know us to prove. If we look at, it's p squared plus p plus 2 times x squared minus 2 times p plus 1 x plus p equals 0. So that part done. Now we get on with this part B. Let C, D be two non-zero real numbers, and let fx equal x cubed plus 2x squared plus minus dx plus cd. It is given that x minus c is a factor of fx, that the remainder when fx is divided by x minus d is cd. Find the value of c and d. Let's do that first. Okay, so that c, d are not real. Then fx is given x cubed plus 2x plus 2x minus dx equals 0. It's xc is a factor. Remainder theorem or factor theorem, fc should be 0. So fc, I substitute x equals c cubed, because of x is there, is c cubed plus 2c squared minus d times c, or cd, plus cd. The cd cancelled out, is all we have, c cubed plus 2c squared. Take c squared out, c plus 2, that is equal to 0. From that, c cannot be 0 because we have been given reminder, x is given that x is a factor, reminder divided by x is cd. Find the value of cd. All right, at the beginning. Then let's see c and d be two non-zero values, so non-zero constants. So therefore, c cannot be 0. So c only minus 2. So that c found. Then they gave us remainder is cd when x minus, when the function divided by x minus d. Again, same fd, the remainder theorem fd, the whatever left with will be cd. So this is the remainder, that is cd. If we could substitute substitute the value x for d, fd is d cubed plus 2d squared minus d times c. C is d now. Sorry, x is d. So d squared minus cd. And equal is a remainder. That is the remainder. So fd is the remainder, because it says that CD is given. So that is CD. Now CD is CD. If you bring that CD to this side, it will cancel out. So what we left with, d cubed, and 2d squared minus d squared is 1d squared. So d cubed plus d squared equals 0, and d squared times d plus 1 is 0. Again, d isn't 0. Non-zero is d. Therefore, d equal minus 1. So c equal minus 2, d equal minus 1. So that's done. Some more reminder, okay, cd values. Right, the last part. For these values of c and d, find the remainder when fx is divided by x plus 2 squared. Okay. Right, so fx is x cubed plus 2x and minus dx plus cd, but we know the value c and d. Therefore, x cubed, they ask us to use the values x cubed plus 2x squared plus d is minus 1, so minus minus plus, so x plus 2. So they said when you divide x plus 2, then the remainder, right? X plus divided by x plus 2 squared. We know that fx, the actual given function, is the third order function or third order polynomial, and divided by x plus 2 squared is a second order polynomial. So if you divide third order divided by second order, we have the answer for the first order, and the remainder is first order too. So we don't need to worry about the actual answer come up. all we are interested in remainder. So remainder must be first order, because a third order divided by second order, remainder has to be the first order. So the standard format of first order, ax plus b. A and b are constant, which we need to find. If you do find the a and b, then job done. So rewriting it, x cubed plus 2x squared plus x plus 2, and that is equal x plus 2 squared, and this the actual answer. When you divide it, you have an answer come up, and you do a long division or whatever, it can come up qx. We don't need to worry about it, or just go through it and then you'll understand. And the remainder, of course, ax plus b. So because x plus 2 is second order, the qx must be first order. As I said, we don't have to worry about first order, second order. It's a function of x, definitely, because of third order divided by second order. So that should be a function of first order in this case, or function. And the remainder is a first order ax plus b. We have to find a and b. Right, so we have an equation formed up. So just put it x equal minus 2, because we know for sure that x plus 2 becomes 0. So simplified, we don't need to worry about q. So x equal minus 2, the left-hand side minus 8, plus 8, minus 2, plus 2. Left-hand side is 0, so it's just another indication, another finding. X plus 2 is one of the roots. We don't need to worry about. So that is 0. And the right-hand side, if you put it that the x plus 2 is 0, so we need everything, the first part is gone to 0, minus 2a plus b, minus 2a plus b. So minus 2a plus b is 0, one equation. Having got this equation, then we try and try and find another equation. So what I did here, I differentiate both sides just to get it, because of both sides the function, we do anything, just it's simply differentiate, it will be good. So if I differentiate both sides, and the left-hand side, 3x squared plus 4x plus 1. I'm not going through the differentiation. The students should know about it. And then this is the first part is multiple. So x plus 2 squared, and the differentiation of qx, and I put q dash plus qx time differentiation x plus 2 squared. So there's 2 times x plus 2, differentiation x is 1. Then ax plus b, differentiate ax plus b, just a. Again, we need to eliminate that q and then the first part and the second part, because if you do apply that to minus 2, then we don't need to worry about the qx. So x equal minus 2 again. Left-hand side, 3 times 4, 12, minus 4 times 2 is minus 8. Minus 2 is minus 8, plus 1. Equal, the other side, x plus 2 is 0, another x plus 2 is 0, so just we do not worry about the first two terms, only we have, or we left with a. So a is the right-hand side, this is 12 minus 8 plus 1, 12 minus 8 is 4, plus 1 is 5. So a equal 5. And then we know the first equation, 2a minus b is 0, 2a minus 0 is 0, and b equal 10. Then the remainder, ax plus b, which is 5x plus 10, is quite a work-hard question. Is mainly remainder theorem and quadratic functions, and then its properties. Thank you. Please subscribe the channel and share the contents with your friends and fellow students, and whoever preparing for the final exam. Please share this with them. Thank you.